So this is the title of the talk. Many of you may have encountered the name of this person. I will be mispronouncing it as Fourier throughout the talk because that's how we pronounce it in India. For a better pronunciation, you should ask some professor from Columbia University. Okay. So let's take you can see the period in which he lived, which is actually quite important. In fact, I can give you a surefire recipe for becoming one of the immortals in optics and related themes. You should be born in France, and your name should begin with F. Okay, so you can be a Fermat, a Fizeau, a Foucault, or a Fourier, anyone else. That's all you have to do. I think I even missed one or two. But so this is what he looked like before photography, and a little bit about his. It's interesting that he came from what we would call a humble background. So although this is France before the revolution, they still had an educational system where a person who was not very well off. In fact, he lost his father at the age of 9. The father married twice. He had 3 children by the first wife and 15 by the second. I think Fourier was number 12. So now you know what is meant by a Fourier series. Again, if you know your French history, all kinds of things happened around 1790 when he was just the right age to get involved in politics. Of course, he was one of the common people. So they were the ones who were going to win. You know, they were going to take all these aristocrats, like Lavoisier, for example, was guillotine, the famous chemist, right? So you would think that he would be safe. But what happens is that once these guys have finished all the aristocrats, they start finishing off each other, okay? But he somehow escaped, and then he joined the military. Incidentally, those military schools were fantastic. I mean, many great scientists learned what they learned in military schools in France. And Napoleon made him a governor, and that is the period. So just think what is happening in someone sitting in Raj Bhavan and writing a serious treatise on heat conduction, right? And we will see that, I mean, it was path-breaking, but it was not fully accepted, and we will also see why, okay? So his motivation was the conduction of heat. So I could just spring this equation on you, right? So theta is the temperature. Imagine that you just have a rod, okay? So x is your position along the rod, and t is time. So you set up some temperature distribution in the rod, and maybe you put one end in ice and you put the other end in steam. I think we used to do that sort of thing. But you have some distribution of temperature, and it might change with time. So you need an equation which tells you how it changes with time. And interestingly, this equation tells you that the way it changes with time is related to how it changes in space. Okay? Now, I don't want to make too much of a mystery out of it. So I will do what Kripa did for you. We will convert this equation to a form in which you could put it on a computer, right? So immediately x has to have some discrete values separated by delta x, and t has to have some discrete values separated by delta t. And of course, we are making an approximation, right? So this time derivative will now just be the difference of 2 values, right? Right. So this time derivative is just saying sit at the same point x, but allow time to increase by delta t, look at the change in temperature and divide by delta t. So that's what this left-hand side means, this partial derivative. Now k is some constant. Now the right-hand side is the second derivative. So what we do is we open a large bracket, put a delta x in the denominator, and put the variation of the first derivative, okay? That's how you get the second derivative, by differentiating the first derivative. Now, if you look at this is the first derivative. So same time, everything on the right-hand side is the same time. And you have something at delta x and something at x. So let us say that this is a good estimate of the first derivative at the midpoint, x plus delta x divided by 2. Now what about this? This is an estimate of the first derivative again. Now between x and x minus delta x. So imagine that this lives at x minus delta x by 2. So this lives at x plus delta x by 2, this lives at x minus delta x by 2, right? So we have evaluated the first derivative at 2 points which are separated by delta x, and that's how this becomes the second derivative. And you could actually use this. If someone gave you temperature as a function of position, right, at 0 time, then you could use this equation on a computer in the way that Kripa showed you, and you could keep evolving it. But what's the meaning of this? Okay, well, it's you should think why would the temperature change at a given point? Okay, at x, only if more heat is coming in. Take a delta x region. If more heat is coming in than is going out, then the temperature will go up. Okay, so this is where something called Fourier's law of heat conduction comes in. It's a fairly reasonable law. What he says is, okay, maybe I'll draw a small sketch. We have x plus delta x, x minus delta x. So let us say this region belongs to x, okay? And you have a derivative. So if this is hotter than this, you expect energy to flow this way, right? Likewise, if this is hotter than this, you expect energy to flow this way. That's something called Newton's law of cooling. You might have used it in calorimetry, except this is now adapted to a situation of a continuous medium, not just your calorimeter in the outside world, okay? So this is actually Fourier's law of heat conduction. And he conducted experiments. He didn't just write this law down and satisfied himself that this is a reasonable law, okay? So this is the heat flowing in from the left, if you like. I mean, from, I guess, delta x, okay, x plus delta x, so flowing in from the right. And this is the heat leaving from the left. So that's the justification for this equation. I cannot leave this topic without mentioning that, yeah, temperature gradient is the first derivative. Without mentioning that one of my ICTS colleagues, Abhishek Dhar, has, must be the expert on every way that this law could break down, okay? But in many situations, the law actually works, okay? All right, so what do you do with an equation like this? And certainly in around 1800, people had got comfortable with ordinary differential equations, but they were still exploring partial differential equations like this, right? So what Fourier did was he first looked at a special solution. So I'm going to put this up, and you will encounter this trick more than once in your future study of physics. You have a function of two variables, x and t. You say, let's just imagine that is the product of some function of t, f, and some other function of x, which is g. Now, are you all convinced that not every function can be written like this? Well, one way to see that is, again, go back to the computer, right? So now x and t are points on a two-dimensional grid, right? So if you had a general function of x and t, let's say n by n, then you would write down n square independent numbers, right? That's a general function of x and t. But look at this factorized form. F of t has n numbers, g of x has another n numbers, and that's it. So since 2n is definitely not n squared, this kind of function is going to be much more special than the most general function. But right now, you have to begin somewhere. So why not try and look for a solution like this, okay? That's the theme of the lecture. That's the theme of the lecture. So, can I, instead of reading it out and so on, why don't you people quickly plug in this theta of xt into the heat conduction equation, and the left-hand side, only f gets differentiated, and on the right-hand side, only g gets differentiated, right? Because these are partial derivatives. And for convenience, I've taken k as 1. And as I told you a week ago, you can always pick the units so that k is 1. Maybe some strange units for length and time. So far, so good? Then you pull all the f's to the left and all the g's to the right. And this is the point to mention that I think I've already given the PDF of this lecture to Disha. If she has already uploaded it, then actually you can start studying that instead of listening to my lecture. But otherwise, you don't have to worry about jotting down everything. That's all, just to tell you that. Huh? Now, this is a very interesting equation after you've done this rearrangement, because on the left-hand side, you have something which is only a function of time. On the right-hand side, you have something which is only a function of x. How can this happen? Right. Both of them have to be constants, right? All right. Now, I want to say something about this constant. I would like to call this constant minus alpha squared, and alpha is real, so this constant is negative. And so look at the left-hand side. If you look at 1 over f df dt equals minus alpha squared, can anyone quickly solve it for me? Yeah, df dt is minus alpha squared f. F is a function of time. No, alpha I told you is real. This is positive. So if you had exponential of some real quantity, if you kept differentiating it, you wouldn't get a minus sign, no? Okay, let me take alpha also as 1 for the moment. So which function, when differentiated twice, becomes minus of itself? Ah, that's right, sine and cos. Yes, yes, oscillations and all that. I mean, surely. I'm happy someone mentioned exponential because that explains why you want this to be negative, right? If you had chosen it with the other sign, you would have exponential of alpha t as one of the possible solutions. Somehow it doesn't seem reasonable that I set up this rod with, you know, ice here and steam there, and the temperature just goes on shooting up, right? So now how about the other side? So we now know, what about so f, by the way, how about the spatial part? Right? So, okay, sorry, the f equation has a minus alpha squared. It is an exponential, I apologize. Exponential minus alpha squared t, first order. And whatever I said applies to the second equation. D square g dx square is minus alpha squared g. Sorry, huh? Yeah, d square g dx square. So this is the one whose solution is trigonometric functions. And it's the second order equation, so you have these constants. Okay, so that's how sines and cosines enter the picture. So this is, let's take one of the, so if you had a rod and you were lucky enough that the temperature distribution was some cosine of alpha, then you have got your solution. You just multiply it by exponential minus alpha squared into time, and you have got a solution. But the question that Sam raised, what's the general solution, right? Now, you might have come across the term linear. What this simply means in this context is that someone gives you a theta 1. I'm going to write an abbreviated form of this equation. Partial derivative with respect to t is k times theta 1 partial derivative twice with respect to x. And similarly, if one had something with theta 2, which I won't even write, then you're allowed to add theta 1 plus theta 2. That will also be a solution. So therefore, you can certainly manufacture a more general solution, right? Maybe even with different values of alpha. But every sine alpha x and cos alpha x has to be accompanied by an exponential minus alpha squared into time. So that's the recipe. Okay. Now that's fine, but if you come to the lab and you find some distribution of temperature on this rod, can you represent it in this way? That's the big question, right? So at 0 time, don't worry about this exponential minus alpha squared t, because that's always 1, right? But expand it in terms of sines and cosines. And then at later times, each sine and cosine gets its exponential damping term. So that's the way to solve the heat conduction equation, provided your initial distribution. So Fourier said, yes, I can do it. You give me a distribution with respect to x. I will produce for you a series with sines and cosines, which represents that. And if this is the initial distribution of heat in the rod, I will tell you what happens at future times. So let's just see how this works. So for that, we'll have to familiarize ourselves, or I'm sure you're already familiar, so maybe just review the notion, two notions. One is periodic functions. So if you take, if your days can be numbered 1, 2, 3, and it keeps going, but the name of the day keeps repeating every 7 days, right? Days of the week. So that's an example of a periodic function, where the value of the function is just a word like Wednesday or Sunday or something. But every 7 days it repeats. Kepler orbit, the elliptical orbit of a planet around the sun, when it's not being disturbed by other planets, right? In the case of our Earth, every 1 year, you look at it, it's in the same place, right? And doesn't have to be in any special place, right? So if this is the orbit, it's here, you can close your eyes, wait for 1 year, and it'll come back here. If it happened to be here, it'll come back there. So everything, r, theta, all these parameters will repeat. So that simple pendulum is another example. It repeats at the period. So the definition is that this function has a period, which is capital T, and you can take any value of small t and look at the value of the function, that's f of t, and then move by capital T, the period, and you will get the same value. An important thing is for every value of t, right? So that's a periodic function. But of course, it doesn't have to be a sine and cosine. Now, I've written down 2 periodic functions, which we'll be using. One is sine of 2 pi, n is an integer. I'm taking it to be either 0 or a positive integer. And capital T is the period. So first, let's look at n equal to 1. So you have 2 pi into small t over capital T. So what happens when small t increases by capital T, right? This becomes 1. I mean, this increases by 1. So whatever is sitting inside the sine increases by 2 pi. Likewise in the cosine. If you have an n here, then it increases by n times 2 pi. But trigonometric functions always come back to the same value when the angle increases by 2 pi or any multiple of 2 pi. So these are good examples of periodic functions which have been constructed so that the period is capital T. Now, I'm going to use the word frequency, and there are 2 kinds of frequencies you encounter in the studies of physics. The more popular one seems to be angular frequency, which is omega, which is radians per second. But I'm going to use the old-fashioned cycles per second. So capital T is the duration of one cycle, right? That's why when we increase by capital T. So if you ask what are the frequencies of these, the frequencies are n divided by capital T. So let's take the n equal to 1, for example. So the frequency is just 1 over capital T. And the general formula is 2 pi into the time into the frequency, the fundamental frequency 1 over 2, and then you can take any integer multiple of that. Because an integer multiple of 2 pi also brings trigonometric functions back to the same value. So there's not if you give n these integer values, you can, of course, if you looked at any one of these, you could say the period is, is shorter than capital T. But if you have a number of them with different values of n, and starting with n equal to 1, then 1 over T is called the fundamental frequency, and n over T is called the nth harmonic. So this fundamental and harmonic is terminology from music, I believe. So these are the frequencies. Now, purely for, this is another point that the period is capital T, so do we have to take it from 0 to capital T? And the answer is no. So I'll try and draw a periodic function. Okay, this is capital T, and in the next capital T, even if it doesn't exactly look like that, please believe me that this is meant to look the same, and so on, okay? So you may say, okay, I need to have it from 0 to capital T. On the other hand, just imagine that you took some point here, and you take the corresponding point here. This could be T by 2 for it. And then this would be 3T by 2. You will notice that all that has happened is, you may say, okay, I only have this part of the function. But this part is now given to you here. So if I gave you the function only between these two limits, you could reconstruct between 0 and T, right? So there's nothing special about 0 and T. And in fact, for my convenience, I'm going to choose an interval minus T by 2 to plus T by 2. There's another way of thinking about it, which is very natural if you think of the days of the week. You think of the function, this x, as actually going from 0 to 2 pi, but think of it as a circle, okay? So then it's absolutely natural that, I mean, you have a function. Now, how do I sketch a function when I've bent the x-axis like this? So I'm going to do some, so please think of this as the graph of the function. And obviously, it doesn't matter where you start, right? You can get the whole function. So periodic functions can also be thought of as living on a circle. Now, just to save myself writing a lot of 2 pi's, I'm going to choose the period equal to 2 pi. So we are now talking of cos n times small t and sin n small t as our examples of functions with a period 2 pi over capital T, with a frequency, I have said this already. Now, when I prepared this lecture, I put in symmetric and antisymmetric, and then I realized that you might also have encountered this distinction in terms of even and odd. So that again, best illustrated by a sketch. So minus T by 2, T by 2. So this is an example of a symmetric or a even function. So if you know the value at small t, then you get exactly the same value at. So you can think of it as taking the function from 0 to T by 2 and reflecting it. Okay. And the other kind of function is the antisymmetric or odd function, right? Which might look like this. So if you have the value at t, you go at minus t, you see minus of this value. Okay, so this is an example of a even function. This is an example of a odd function. So classic example is cosine would be even because cos of minus theta is cos of theta, and sine would be odd. And the same holds for cos n theta and sine n theta. Right, so that's the definition. Then you can actually take any function and break it up into a symmetric part and antisymmetric part. I've just written it out here. So take f of t and add f of minus t and divide by 2 and let little t go all the way from minus the same interval that we talked about. So what happens if I change t to minus t on the right hand side? Nothing happens. These two get interchanged. Okay? So this is clearly a symmetric function. You put a minus sign here and you change t to minus t, then of course this whole thing changes sign, right? because f of, this becomes f of minus t and this becomes f of t. So this is an antisymmetric function. And I've put by 2 here so that if you add up these two, you'll get back your original f of t. Right? That's all. That's all there is to it. So now this is what Fourier did. He took this function, which is temperature along the rod at 0 time, and then he first broke it into a symmetric part and an antisymmetric part. And the symmetric part was represented as a sum of cosines with a period of 2 pi, because we have said our period is 2 pi. So think of the length of your rod as 2 pi, okay? With some coefficients which are unknown at this time. And then you have the antisymmetric part of the function, which is sines. So this A0 is the constant part, which is of course symmetric, right? Okay. So this is what is called the Fourier series. But of course, the important thing is to find out what the coefficients are. So this A0, so we'll look at an important property of cosine and sin x, especially when you see them in an interval from minus pi to plus pi, or 0 to 2 pi. For every positive value, there is an equal negative value which cancels. And that is true of sine, true of cosine, okay? So when you take an average, this entire part doesn't contribute, you just get A0. Okay? Or the other way to think about it is just integrate both the left-hand sides and right-hand sides from minus pi to pi, okay, of f of x. Then all these will give you 0, okay? I mean, the cost, I mean, you know that. Only this will give you 2 pi times A0, because you will have an A0 and you will be integrating it. So then A0 itself is this, okay? So something similar can be done to find all the other coefficients, okay? So let me just do it. This is not very visible, right? So I can do some erasing. So now the idea is to multiply this f of x by sine, let's say sine of p times x. P is some integer. Integrate from minus pi to plus pi. Right? So what would happen? There'll be the A0 term, but if you multiply it by sine px and integrate, you'll get 0. Okay. Similarly, if you take sine px and multiply it by any of the cos terms, you will get 0. Even if you write sine px sine nx, right? This is, if I remember my trigonometry, it's half of, half of cos p plus n x. Yeah, okay, I'll write it and then check that it's correct. Cos of p minus x. So you have the product of two sines which occurs with an a. Yeah, I think this is correct, right? So again, when you integrate over minus pi to plus pi, you would think everything will become 0, right? But that's not true. The only case where it doesn't happen is when you have p equal to n. Then, of course, this is just 1. And 1 with a half integrated will give you pi. So that's the basic idea. And so if you carry out this operation, you can get the values of all the a's and all the b's. So in this case, you will get pi times AP, and in this case, you will get pi times BP. So this is now, so if you want all these coefficients, what you have to do is to take your function, whatever it is, multiply by sine and cos, not just of the fundamental frequency, but of all the harmonics, integrate, divide by pi in most cases, but 2 pi in the case of A0, right? So we now know how to calculate these coefficients. I'm not actually going to do it, but I'm going to take a particular case. So the particular case I'm going to take is called a square wave. Okay. So it's a function. I'm just calling it SQ of x. Lives between minus pi and plus pi. For x, strictly between minus pi and 0, which means it doesn't take any of those two values, but takes every value in between. We are going to say it's minus 1. And for x strictly between 0 and pi, we are going to say it's plus 1. And exactly at 0, we are going to say it is 0. And at plus or minus pi, we are going to say it is again 0. Because that is what would make it an. So this is what the graph looks like. I should really have a dot somewhere here to tell you that the value is 0 when x equal to 0. I think the dot's probably too small to be seen. So this is what a square wave is. So now it's a simple exercise of integration. Multiply the square wave by sine x, sine 2x, sine 3x, cos x, cos 2x, cos 3x. Integrate and calculate all these coefficients. Right? So I'm assuming that one can do that. But you can already see this is a odd function, antisymmetric function. So cos does not have any business to be in the Fourier series, right? So you will only have the sine terms. And there even interestingly, you will only have the sine of odd multiples. You will have sine x and then you will have sine 3x. If you think about it a little more, sine 2x will already go through one full cycle here and it will cancel off, likewise here. So that's a little bit of justification for my, I'm just following the recipe for calculating these coefficients. There's also a 4 somewhere. So 0, A0 is 0, 4 over pi, sine x, sine 3x divided by 3, sine 5x divided by 5. So this is a calculation, which I'm sure those of you who are curious can carry out. But I'm also saying that this is the temperature distribution at 0 time. So this is a kind of discontinuous distribution. So it's as if someone, in fact, we can think of this as a ring, right? So one semicircle of the ring is being kept at a temperature of +1, and the other semicircle is being kept at a temperature of -1. And at the place where two of them meet, you have a jump in temperature, okay? Incidentally, what value you put here at this single point will not affect the value of any of the integrals that we have talked about, okay? We talked about integral of fx into sine x or fx into cos x and so on. Okay, so this is at 0 time. So what's going to happen at a later time? Every one of these, you'll have to look at the value of alpha. Alpha is 1 here, 3 here, 5 here. You'll get an exponential minus alpha squared into time. Right? So here it is, sine x exponential minus t, and of course divided by 1. Sine 3x is 9. So what does one do with such an expression? Okay. Now, of course, Fourier did not have access to the resources we have, and in particular, Kripa gave you this nice lecture on how you can take a function and just plot it, right? Using Kripa and I were colleagues in Azim Premji University, so she forced me to learn Python. But my native language happens to be something else, which is called GNU Octave. So no libraries need to be imported. That's one up for me with respect to Kripa. But you'll recognize many of the familiar constructs which you saw. I think you saw linspace, you saw that. You saw for, but one of the nice things about Octave is it also tells you when the for ends. So that's all that's happening. We've got some 2001 points going from minus pi to plus pi. And then you have this inner for, right? There should be one more end for there. You 4 over pi, sine of something divided by n, sine of nx divided by n, and you have exponential minus. That's it. You do it, and in fact, you're looping through different values of t. I'm not going to run this program, but if I ran it, it would show you how this function keeps changing with time. So what I've done is, I'll show you the pictures one by one. That's it. So this is the starting point. By the way, you might have noticed I took 500 terms in the Fourier series. I didn't take an infinite number of terms. And it's representing the square wave, except something funny is happening wherever it's discontinuous, okay? We'll keep that aside for a later discussion, okay? The Fourier series seems to be struggling just at the points where, so even after 500 things, it's not looking so nice here and here. But the moment I take a small value of time, say t equal to 0.01, what would happen? If t is 0.1 by 100, then when n is 10, n squared into t will already be 1. Exponential of -1 is some, I don't know, 36% or something like that. So already n equal to 10 is being killed by 36%, and higher n's are being killed more and more, right? So now you can see that the temperature distribution, I mean, the hottest part is still hot, and the reason is simple. Here, the temperature gradient was 0. Therefore, according to Fourier, no heat is flowing back and forth here. Of course, here you have some kind of infinite gradient, okay? So what has now happened is, you've got a finite gradient here. Heat is flowing from here to here, but these parts are unaffected at t equal to 0.01. Go to a slightly later time. I think there's still some small part here, but now you have a heat flowing from here to here. And now what will happen as we go to a still greater time, 0.5, is the temperature has now fallen below 1 here, and this is risen above -1 here, right? So the temperature is tending to equalize. I mean, physically this makes complete sense, right? And by the time you come to t equal to 2, you, first of all, the temperature differences have become much less. And also you see the shape is a sine curve. And the reason is everything except n equal to 1 has got killed by that exponential factor. So I just thought I'll show you one example of how the heat conduction equation works. Somewhat artificial example, but there you are. Now, get back to some history. You already saw something strange was happening at the discontinuities, which if you're a physicist, you say, okay, maybe I'll take some more terms and it'll all go away and so on. But Fourier had to contend with some of the best mathematicians of his time. So when he sat in this province and wrote this treatise, he had to send it to Paris, and it was refereed by some major mathematicians. And this is what they wrote. The manner in which the author arrives at these equations is not exempt of difficulties, and that his analysis to integrate them still leaves something to be desired on the score of generality and even rigor. So who are these guys? These are mathematicians, so their names do not have to begin with F. These are Laplace, Lagrange, Legendre, and Monge. I mean, if you've studied 19th century mathematics, you'll know that they were. So actually, it didn't get published, okay? Then later on, some other people came, and they realized there's a lot of truth in what he has done. So they wrote their papers, which appeared before Fourier's papers, and he was naturally quite upset. So he wrote about these gentlemen. One does not extend the bounds of science by presenting in a form said to be different, he's being sarcastic now, results which one has not found oneself, and above all by forestalling the true author in publication. So if you thought that all these French mathematicians were one happy family, then you can see that they were not so, okay? So these are the people. Poisson you must have heard of, I think. Biot is better known in physics, actually. Biot-Savart law and all that. So anyway, they had their disputes. But gradually people came to understand what was going on a little better. And one of the nice pieces of understanding was contributed by an American physicist, maybe the first American theoretical physicist, called Gibbs, right? So what he was able to prove is that you can, I went up to 500, but suppose you go up to n, some capital N, which is huge. You sum up the Fourier series up to capital N, okay? Then you'll always get this error at that point of discontinuity, and the error won't go down. It's an 18% error, actually. In this case, I checked. Nevertheless, it's true that the series converges for every value of x. Now, how can this be? Of course, at x equal to 0, it converges because everything is 0, right? So this is the true value, but there is an error term which looks like this. And this is 18%. So what happens is as n increases, this keeps shrinking and keeps moving to the left. So at any point, sooner or later, it will pass. And then the series will converge. Okay? So anyway, Gibbs was the person who pointed this out, and people had not realized that at that point. So this is just an interesting. And you may have assigned any value at 0, but the Fourier series will give you 0. Right? So I just thought I'll comment on this, because it's an interesting property of Fourier series when there's a discontinuity. Now, the method which is used to find these Fourier coefficients is some magic, right? You just multiply both sides by sine p of x and so on. But later on, I think people acquired a bigger perspective and connected it to something which you're all familiar with, which is the notion of a dot product. Okay. So, just let's work in 3 dimensions, good old 3-dimensional space. You have some vector r, and you would like to expand it in terms of I, j, and k. So how will you find this coefficient a? Just do r dot I, and r dot I will give you a into I dot I, which is 1, and b into I dot j, and c into I dot k, which is 0. Okay. So the way to extract the coefficient is to take the dot product with the vector which you are, the component which you are interested in. And this is the reason why it works. So these 3 vectors, I hat, j hat, k hat, are called orthonormal. So if your doctor says you're orthonormal, it means that all your bones are in good shape. But in this case, it simply means that each one of these vectors, its dot product with itself is 1, and its dot product with the others is 0. Now you can see that that's exactly what happened when we found the Fourier coefficients. So again, let me go to the board. So what happens when you do something like this? Integral fx cos of px dx. Again, let's go to the computer. Right? Let's divide the range of x into a number of points. So you have values of f at all these points. Right? And then you have values of sine at all these points, or cos px. Okay, so it probably looks like this. I mean, this is p equal to 1, but it could be anything. So again, you have, since we have made x discrete, you have all these values. And then how do you calculate the integral? Take this value of f, multiply by this. Take this, multiply by this. So clearly the values of f and the values of cos x can be treated as the components of some high dimensional vector. And you're doing nothing but taking the dot product. So the trick will work if, so this is our equivalent of that I hat. And maybe this next one, right, is the equivalent of j hat. So these should be orthonormal. That means if you multiply 2 of them with each other and integrate, you should get 0, which is the property we used. So basically the perspective which people got later, I do not know if Fourier had it himself. So it's a very natural rule. Once you recognize that the constant term, the cosine with the fundamental and all the harmonics, the sine with the fundamental, all the harmonics, can be thought of as different vectors which are all orthogonal to each other. If you multiply any 2 and integrate, you get 0. Of course, you may ask, are they normalized? I think we got pi by 2, or no, we got pi. But that's okay, that pi can easily be taken care of. So this perspective on Fourier series took a while. And now there's a flourishing branch of mathematics called functional analysis, where I won't tell you more about it, except you think of functions as vectors in some space. And this is especially useful when you get to study quantum mechanics, because you have all these wave functions, right? And it's useful to think of them as vectors. And curiously, all this was developed in 1920s by mathematicians. And one great man called Hilbert gave some lectures, and maybe slightly less great man called Courant took the notes, and they published a book called Courant and Hilbert, which had all this theory of Fourier series and all the generalizations to sets of functions and so on. And it was all ready-made for the people who were going to do quantum mechanics in the 1925 and later. Okay. Now, you see how I'm doing for time? Started at 2, and yeah, I think I do have enough time. So, I want to put back the period capital T. And this is just going to be a straightforward repetition of what we did earlier, V0. And now you have 1 over T as the fundamental and N over T as the nth harmonic. Okay? Same, you have cos, you have sine. So this is now the Fourier series which goes from minus T by 2 to plus T by 2. So again, A0, we had 2 pi last time and now we have T. Same formula. And these functions are still orthonormal or whatever it is. Except now if you take cos square or sine square and you integrate it from minus T by 2 to plus T by 2, you will just get T. You will get half T because the average value of cos square and sine square is half. So that's why we have this half T coming here. So this is really going back to the case of a function with general period, not 2 pi. Now, the reason why I'm doing this so let's say we have some function living here, and let's say it also falls off. We're not going to change this function, but we're going to take this period and keep pushing it further and further. So then what happens to the allowed frequencies, right? The frequencies are 1 over T, 2 over T, etc., right? So these will be the Fourier coefficients of that function. So if you push T to infinity, in some sense you have forgotten the fact that it's a periodic function, because the remaining copies of this function have been just pushed out to infinity. By the way, this is, I hope the ICTS has excellent mathematicians. I just hope none of them are in the audience, because this is not the way you should do it. But this is a way of motivating or entering the next topic that we'd like to talk about. So we're going to take capital T to infinity. And now these are going to come closer and closer to each other. So you are going to get frequency as being almost a continuous variable. Okay? So N over T we are now going to call as nu. So your cos of 2 pi little t n over capital T is just going to be cos of 2 pi nu t. That's it. Now the Fourier series is really a sum over terms for each of these. But if you have a sum like this, again keep in mind how one evaluates integrals on a computer. Of course, there you start with a continuous function and then you make this discrete. Now we are going to do the opposite. This is discrete, but we are going to imagine that this is an approximation to a continuous function of frequency. That hasn't happened yet. Here, this is just the same Fourier series rewritten for a general period. But now the idea is to think of a function which is not periodic by pushing capital T to infinity. And I have put can be treated with an exclamation mark to give you a warning that this is a way to introduce the subject to you, but certainly when you study it in depth in a mathematics class, it will probably be done in a much nicer way. I can even send you some references on that. Right? So now, since we are going to replace it by an integral, the d nu, the step, is just 1 over t, right? Because nu is n over t. So actually, it's straightforward now to make these substitutions. So what is the Fourier series going to look like? We had a little a and a cos, a little b and a sine, but these were discrete frequencies. Now we have a continuous frequency. We have a capital A and a capital B, which are not little a and little b, but they are proportional to them. Okay? And you have all frequencies going from 0 to infinity. And I can assure you, you get this factor of 2 also when you do the appropriate limits. But then we also had these formulae for little a and little b as a function of n. But n has now become nu, right? So the coefficients, so I put series in quotes, coefficients also in quotes, because now it's not a discrete set of coefficients of fundamental and harmonics. It's a coefficient which is the function of a continuous frequency variable. So this is what it looks like. And you can see this is very similar to the expression we had earlier, right? Except you have 2 pi nu t and you're integrating from minus infinity to plus infinity. So I'm not actually going through the substitutions which would lead you to these two equations, but I can assure you that it's very straightforward. Now the next step is an interesting step. So far, I've been implicitly assuming that everything we are dealing with is real. Okay? But it often happens in mathematics that if you want to simplify a problem, you make it complex. Complex in the sense of using complex numbers. So what you can do in the second set of equations, you could take a plus ib, okay, and call it a single complex coefficient. Right? So that will turn out to be an integral over time, f of t, and now you will have cos of 2 pi nu t plus I sine 2 pi nu t. So again, I don't know how the syllabi go these days, but does that look familiar? Right? So that's what happens to the equation for the coefficients. So you know we have a single complex coefficient. I'll temporarily call it C of nu, which looks like this. Now what about the Fourier series itself? Right? So here you can write it as, you could write it as a plus ib into cos plus I sine, right? Actually cos minus I sine turns out to be the right thing. But you might worry a little bit, right? Because there are some other terms. So the next step which is taken is, I told you that integer n can be taken as 0 or positive, right? There's no need to take a negative n, because cos of minus nt is the same as cos of nt, and sine of minus nt is minus sine of nt, right? So really you don't need anything more than this equation. But it's actually convenient to push nu to negative values and take a to be an even function and b to be an odd function. Then in that case, what happens is some of these extra terms which you don't want cancel, and you get the Fourier series now looks like this. The C of nu e raised to so that's what I have on the next slide. And I think, if I remember right, Sam said lecture on Fourier transforms. So I've reached the Fourier transform. So now there's no trace of any periodic function on anything. Both time and frequency go from minus infinity to plus infinity. So I had a sketch of some function like this. There will be a corresponding function of frequency. And the reason for reaching this stage, obviously we are not going to have a long discussion of these two formulae, but they look very beautiful and very symmetric. I could give you some examples. We have chosen frequency and time, and you also know that in quantum mechanics, frequency is related to energy. Okay, so this kind of equations do relate how things depend on time and how things depend on energy in quantum mechanics. On the other hand, if you had x as one of the variables, okay, so you could have a function of x. Then if you expand it in terms of waves, you would have cos of some k into x, right? And again, I'm sure you would have seen enough quantum mechanics to know that k is related to momentum. Okay? So this kind of relationship, which we have reached somewhat slowly, starting with heat conduction and Fourier series and so on, is actually a very, very universal kind of relationship, often used. So I've given you the two examples in quantum mechanics, but I'll give you a few more. First of all, you could work with other equations of mathematical physics, like the wave equation. So in the wave equation, the left-hand side is not d theta by dt, but d square theta by dt squared. So never mind, I mean, you can still separate the variables, you can go ahead and you can. Then it's also related to some very interesting experimental techniques, okay? So let's take this simple problem of finding the spectrum of a source. Source emits radiation at different frequencies. Some of them might be discrete frequencies, like, you know, the hydrogen spectrum or something. And you want to measure it. So how do we do that? The method that we are normally taught is put it through a prism which separates it, or put it through a grating which again separates the different frequencies. But interestingly, it is actually possible to measure the spectrum of a source without separating the different frequencies. Okay? And the setup is something like this. It is attributed to Michelson. It's called a Michelson interferometer. Right? So what you do is you get interference fringes here, and then you move one of the mirrors. So you're introducing a time delay between the two beams, but you're not separating the different frequencies at all. Then you measure things as a function of time delay. And then if you do a Fourier transform, it actually gives you things as a function of frequency. Okay? I'm just throwing this at you. In fact, this device is called a Fourier transform spectrometer, and it's very convenient to use in infrared and so on, where, you know, making these prisms and gratings and so on. And the beauty is that you're measuring all the frequencies at the same time in some sense. Interestingly, if you go to an MRI machine, I will squeeze you down to one dimension, and they are interested in the number of protons in your body as a function of position. Okay? So for various reasons which we will not get into, these protons have magnetic moments which is flipped over and they all start rotating. Okay? But the protons in different places rotate at different rates because the magnetic field is slightly different. So again, you can see it's going to be a Fourier transform. You're taking the original function, multiplying it by some trigonometric function and integrating. And of course, you must do it for all values. So that's how your image is created in MRI machine. FID is the technical term for free induction decay, which simply means get all these protons to the perpendicular plane and let them go around and let them cancel each other and gradually die out. Now this is, of course, a major theme in physics, that you can measure scattering of X-rays as a function of angle. So it's actually a Fourier series in this case because you get number of spots. And the reason is the crystal is actually a periodic function. So if you think of the electron density in the crystal as a periodic function, this technique of X-ray diffraction gives you the terms in the Fourier series. Well, it's a long story, but it can be used to find the position of atoms in the crystal and say something even about a non-crystal like a glass. And this is, of course, an example which I like. You have radiation coming from the sky. Now, you want to make a map of the sky. So you could make a telescope which has such a narrow beam that it only looks at one point in the sky. But that's impractical. So what you can have are a number of telescopes, each of which looks at a fairly large region of the sky. But then you interfere these telescopes. You combine the signals, right? And you can do it by separating the telescopes, right? So that's the X variable. Or you could do it by having number of telescopes and looking at all possible pairs. That's a technical detail. One is the Fourier transform of the other. So if you're able to measure this correlation between telescopes or interference fringes as a function of the separation of the telescopes, you can do a Fourier transform and get a map of the sky. Okay. And you know, going even further, if one of the major themes in 20th century physics has been that, let us say in condensed matter physics, you can measure two kinds of things. You can measure something which is a function of frequency, right? You might measure the conductivity of something as a function of frequency, you know, put different frequencies and find how the electric conduction is. Now, if you transform that to time, what does it tell you? If you do a Fourier transform, it's with time. Well, it tells you something about, let's say you don't apply an electric field, but you just happen to have some random current. How would that current decay? Okay, so that's called a correlation function. Right? You leave the system alone and just see how the current fluctuates. Okay, and the other is when you disturb the system with the radiation of some frequency, and these are connected by Fourier transform. So just to make it worth your while to study Fourier transforms. So finally, I'll come back to the last but one example, because that's an area of particular interest to me. And I'll just leave you with this picture. After all, we are in one center of TIFR, and another such center is the National Center for Radio Astrophysics. This is one of the telescopes. It's 45 meters in diameter. I told you, you need to correlate pairs of telescopes. So I'm only showing you one of them. There are 30 of them scattered over an area of Western Maharashtra. And so all these correlations are measured. I mean, it's a long story. Signals are combined by optical fibers, and beautiful maps of the sky have been made. So I'd like to leave you with this. After all, it belongs to a sister institute. It's something that even the nation considers as an achievement. And last of all, I did spend a decade here at this place. So again, let me assure you that every time we had summer students coming in to learn how GMRT worked, I would be called in to give a lecture on Fourier transforms, which means the starting point of the lecture would be that last equation which you saw. And so just to make it more, to add a touch, apparently Plato had a board saying, let no one ignorant of geometry enter here. So I put up something which said, let no one ignorant of Fourier transforms leave here. I don't mind how you are when you came in, but I hope you've got something out of this lecture. So, thanks. Okay, oh yes, there's a group here named after this Australian radio astronomer called, is that the group? Ruby Payne Scott. And see, radio astronomers initially used pairs of telescopes. Now again, if you remember Young's experiment, if you have a source somewhere in the sky and there is some path difference, then when you interfere the two telescopes, you could either get constructive or destructive interference, right? And actually, the source naturally rises and sets. So the early experiments in radio astronomy in Australia, they couldn't even afford two telescopes. So they had one telescope which is above the sea on a high cliff. So the radio waves would reach directly and also reflected from the sea. So it's as if there was another radio telescope at the image. And even in the laboratory, in addition to Young's experiment, you know, there's something called Lloyd's experiment, where he put a mirror and therefore he could manage with even a single slit. Okay? So these are the early radio experiments, and she was part of that team. Right? And she was one of the first people to realize that taking the distribution in the sky and you're multiplying it by some sine or cosine, the correct mathematical tool to use is the Fourier transform. So the function which you're interested in is how the intensity varies in the sky as a function of angle. And what you should measure is the interference between two telescopes as a function of separation. Now this principle, of course, took many, many years, but by 1960 it had been perfected in Cambridge, and it won the Nobel Prize for Martin Ryle. It's called aperture synthesis. Okay. Now, when the history of this is hotly debated between Cambridge and Australia, and even within Australia, not many people realized until some people dug up the literature that the first person to actually write down this Fourier transform relationship was Ruby Payne Scott. Actually, it's a 3-author paper, but the other authors clearly acknowledged that she was the one who had a mathematical mind. And of course, the sad part is that she had to give up her job because of a rule which the Australian government had, which is amazing. It's like making scientists into air hostesses, and even air hostesses are not forced nowadays to retire when they get married. But the moment it was revealed that she had got married, they said, okay, you can't work for us. So, and I'm happy to say that there was no such rule in India at the same time, or even 30 years earlier. I mean, many women have been able to work after getting married. But yeah. Yeah.
So can you show the slide for square wave problem, like you gave
sure.
the example? Yeah.
There are two slides which had a square wave.
Yeah. So the first slide that you showed.
Yeah.
Here you can see that the SQ of x is a discontinuous function which is discontinuous at 0.
And incident, also at pi.
Yeah, it also at pi. But here, that like SQ of x is equated to a sine series. But sine is a continuous function, right? So its series would also be a continuous function. So how can you equate like a discontinuous function to a continuous function?
Well, you're actually restating this Gibbs phenomenon. What Gibbs showed is that if you stop the series at any point, then it cannot represent exactly what you're saying. It cannot represent this function. However, in mathematics, it often happens that infinite series can behave in a way that individual terms do not behave. So it is a fact, actually. Okay, so let's think of it a little more deeply. When you say this is a discontinuous function, if you take a value at plus epsilon and minus epsilon and take that difference, that difference doesn't go to 0 as epsilon goes to 0, right? That's what is meant by a discontinuous function. You're bringing these 2 points closer and closer to each other, but the difference. Now, interestingly, the series also has the same property, but there's a tricky point here. You have to sum the series first and then take the limit epsilon goes to 0. Now, what you are saying is, if you don't sum the series, it's a set of continuous functions, right? So, one of the first things one learns in mathematics is beware of interchanging limits. So, in this case, is the limit epsilon going to 0 and n going to infinity.
Sir, could you explain why, like, even though over here there is no, like, continuity at 0, why does the code generated graph show a continuity?
Because the code was at finite n equal to 500.
Trying to define a square wave, right? So doesn't it think change or something?
Again, all right, so I said the series converges at every value, right, of x, which is true. However, again, a little bit of maths jargon, it doesn't converge uniformly. What it means is, I can't find a single value of n that I can make the error smaller than some epsilon for the entire range. So the closer you come to this point, the larger the number of terms you have to take to get an accurate value. So I think I sketched that error term. No? So in fact, that error term is nothing but the sum from n to infinity. So what Gibbs did was he wrote a very clever paper looking at that sum and showing that it always had a maximum. But as I said, it keeps getting pushed So at any value which is not at 0, if you take n sufficiently large, you will get. So I stated in terms of interchange of limits. I think the other jargon for it is the series is not uniformly convergent. Uniform convergence would mean that you can find one n which works for every x. It's not. It's interesting that something I threw in just as a curiosity seems to have excited the most interest. But why not? Because this is also what excited the criticism of all these mathematicians against Fourier. So,
yeah, can I just add that I mean, to just amplify on that, the n that you choose depends on x. It's not n independent of x. If it was independent of x, you would call it uniform convergence. But if n depends on x, it's no longer uniform convergence.
Depends on x and doesn't have an upper bound.
Yeah, right. Yeah.
Looks like we are conducting the summer school for women in mathematics. Right? Anyway, why not? Are some of you going to attend that school as well? I'm just curious, whoever is, okay, reasonable number, yeah. In fact, I had a conversation with Shiva Treya and he said, look, at the first year stage, the two subjects, at least the theoretical side of physics and the kind of maths they deal with are not that different. So I'm not surprised by that. So I'd be happy to hear that some people verified these coefficients. It's very straightforward, just do some integrals.